going to take a look at a menu and how to approach curve sketching, because curves are a good way of solving inequalities as well. You can use the graph, the picture, to do it. So let's talk about a curve sketching menu. And I guess in particular for this one, I'm talking more about ones where you've got rational functions. So it might involve a fraction with some polynomial on top and some polynomial on the bottom. So the first thing to do would be to rewrite it as one complete fraction. Find your y-intercepts, they're always easy to find. Sub in x equals 0, what's the answer? X-intercepts, well, that's when the numerator equals 0, depending on how they factorise, whether that's easy or hard to find. Do yourself a polynomial division then. So divide the numerator by the denominator, because once you have it in that form, remember polynomial division, when you divide the polynomial you get a quotient plus some remainder which will be over that original denominator. But that tells us a lot of information. The bottom of the fraction, well, we know that can't equal 0, so that'll allow us to find vertical asymptotes. The quotient will turn out to be the horizontal or the oblique asymptote. Horizontal if it's a constant number, oblique if it's a linear function. I suppose theoretically if it was a quadratic you could have a quadratic asymptote as well. Remember, the horizontal or the oblique asymptote is just telling you what happens out at the extremities of the graph, what happens at positive infinity and minus infinity. And the final piece of information is to do with the numerator. Because unlike vertical asymptotes, curves can cut horizontal and oblique asymptotes. How do we find out where? Well, it's when that top of the fraction, that remainder, equals 0. If that's got a solution, then that's where it will cut, the horizontal or the oblique asymptote. Symmetry. Is it an odd function? Is it an even function? If you know that, you really only have to draw half of the graph if you think about it, because then you just reflect or rotate depending on whether it's odd or even. Symmetry in y equals x, that one's not always as easy to pick up, but basically if you can swap the x and the y's around and you get exactly the same function, then you know the curve is symmetric in y equals x. The hyperbola, I guess, is the easiest one to think about. If you were to swap x and y around, so y equals 1 and x becomes x equals 1 and y, you could rearrange that to get the same graph. And if you have a look at the graph, sure enough, that is symmetric in y equals x. Bit of a note about the asymptotes then. So vertical asymptotes, they're exclusions in the domain, and as I said, you cannot touch or cut a vertical asymptote. It's not in the domain, so it's impossible for the curve to exist there. Whereas the horizontal, or oblique ones for that matter, they can cut them. What happens is it converges. So when a function gets close to a particular number, we say it converges to that value. Now there are 3 limits that are really useful when you want to work out horizontal asymptotes. This one we know, the limit as x approaches plus or minus infinity of the hyperbola 1 on x is equal to 0. If you look at the graph we can see that. As x is getting very, very big, or very, very big in the negative direction, we can see that the curve is getting closer and closer to a y value of 0. But the other ones that are useful are the exponentials. What I call the backwards exponential, e to the negative x. Again, if you think of that graph, it comes down, and again, as x is getting very, very big, it's getting closer and closer to 0. The reverse of that is the actual exponential itself, e to the x, and it's the opposite effect. In the negatives, when the negatives are getting really, really big, that's approaching 0. So if I had to draw this graph, x squared plus x, or 1 minus x squared, and I, for some reason, didn't want to do a polynomial division, I could just look at the limit and go, well, what's happening to this as x approaches infinity? Now, I guess the traditional way of doing it is dividing everything by the highest power. So I divide everything by x squared, because as soon as I try to substitute, I mean you can't actually substitute infinity, but as soon as I try to substitute into the bottom of the fraction, so all those x squareds, I know it's going to approach 0. That therefore means what I have is 1 plus 0 and 0 minus 1, it's minus 1. I say that's the traditional way. The quick way of doing it is, what we always end up with is just the coefficients of that highest power. So on the top, x squared, and on the bottom, minus x squared. X squared is the highest power in this thing. So I just look at those coefficients. Coefficient of x squared on the top is 1, coefficient of x squared on the bottom is negative 1, 1 on negative 1, negative 1. Here's one with exponentials. Now, in order to use this limit, I need to get everything with either they're all positive indices or they're all negative indices. Now, in this case, I've got a mixture. I've got an x and I've got a minus x. Which one do I convert it to? Well, x is approaching positive infinity. So I want to use this second limit here, e to the negative x. I want to convert them all to negative indices. How can I do that? Well, if I divide everything by e to the power of x, then that will do that. Because now the e to the x will become 1. E to the minus x becomes e to the minus 2x, and that's fine. It's still a negative exponential. And then on the bottom, that just becomes 2. That now allows me to look at this limit because the e to the negative 2x, it's the backwards exponential, that's going to approach 0 and I'm left with a half. So I know what that one's doing. It's converging to y equals a half. If I had that same fraction, what's happening out at negative infinity? Well, now I want to make use of the third limit here. And that's where everything's got a positive index. So how do I get a positive index? Well, now I'll multiply everything by e to the power of x, and that'll get rid of the negative index. I'll be left with e to the 2x plus 1 over 2e to the 2x. What am I left with? 1 on 0, which is undefined. So that's telling me this is going off to infinity. So 1 divided by 0 we sometimes think of as infinity. So on the left-hand side of this graph, whatever it looks like, we know the curve is just going up and up and up and continuing to go up. Let's look at this example then. We're going to sketch x cubed minus 9x on x squared minus 4. It wants us to indicate the asymptotes, also the intercepts with the axes. To find the y-intercept, we substitute in x equals 0, and if you sub it in, I'll get 0 on the top of negative 4, which is 0. So the y-intercept is y equals 0. I suppose technically it is x equals 0 as well because it's the origin there, but anyway. Solving it for the x-intercepts, that's the top of the fraction equals 0. I get x equals 0 and x equals plus or minus 3. So let's plot those important points in. We get negative 3, we get 0, and we get 3. Let's do our polynomial division. It becomes x minus 5x on x squared minus 4. That tells me that the vertical asymptotes will be at plus or minus 2. Draw those in. Remember, vertical asymptotes, we draw with dotted lines. On a number plane, whenever we draw a line, or any curve for that matter, dotted, we're saying this is not actually part of the graph. This is not included, but it's like a boundary. It helps me draw the graph. I know it's a boundary here. The oblique asymptote, well, if I look at it, that's going to be y equals x. Does the curve meet that oblique asymptote? Well, if we solve the top of the fraction, we get 5x equals 0, we get x equals 0. So we've dotted in y equals x. We actually already knew about x equals 0 because we found that as an x-intercept. But sure enough, that's going to be when it cuts that oblique asymptote. Okay. It is an odd function because if we have a look at it, on the top of the fraction, we have an odd function. On the bottom of the fraction, we have an even function. And even divided by odd gives you odd. Remember, if it's the same type of function you're multiplying or dividing together, you get an even function. If it's a different type of function, you get an odd function. So we've got an odd divided by an even. They're different types of functions. So we will end up with an odd function. That's telling me I've got rotational symmetry. It's got rotational symmetry. Well, let's draw it. That is what it ends up looking like. Remember, you have to go through the intercepts, but you must bend towards the asymptotes. So starting from the left, if it came from the bottom here and went up, it would have to cut this asymptote in order to get to that point. And it's not allowed to do that. Therefore, I know it's contained in this section here. And when I go to the middle one, again, it's got to go through the origin and bend towards these. I suppose it could have done the reflection of that. That's just a matter of testing a point to see is it positive or is it negative to see where that curve goes. And then by the rotational symmetry, I know that it must do this on the right hand side. So we'll add 3b add 3C to our exercises.